In this video, we would be talking about some of the fundamental concepts of topology. The concepts that we would be discussing today requires no special mathematical skills, neither any concept of advanced mathematics. What it requires is a little bit of visualization so that the concepts become more clear. As you can see that we are introducing this topic as a visual introduction to topology. So I would be using charts, graphs, pictures, illustrations, and some simple examples from day-to-day life so that the concepts of topology is much more clearer. So you can sit back today and enjoy this video because it would require very less amount of complex mathematics but more of figures and shapes which would give you a complete understanding of topology. Once you understand these concepts, you can study topology much better. My name is Shaunak and you're watching this video in my channel Physics for Students. A warm welcome to Topology, a visual introduction. So let us first find out that what are the topics that we are covering today. So first we would be covering what are topological objects and how are the features of these objects different from others. What is known as a featureless objects and at all why do we need them? What is called connectivity in terms of topological vocabulary? What is called a path connected or a connected path, and how to fill gaps, and what is called equivalence relation, homology and homology classes. All these concepts are very fundamental and requires no special mathematical skills but mostly visualization and understanding of the concepts. So having laid down the topics, first let us go forward and understand what those topics are all about. So first what we are doing is that we are covering what is known as topological objects. Now in general, if this kind of a figure comes in front of you, what will you think? Yes, it is a hammer which is used for breaking things. Now if I break the hammer into two parts, dividing this hammer, the first question that rises in your mind is that is this hammer capable of breaking things? Similarly, I take a kind of a porous substance where some water would be seeping in. So the question is that is water permeating through this sponge or through this substance? Similarly, if we take a kind of a steel or this kind of a shape which has got a hole inside it, then the question also rises that is this alloy solid or does it have certain bubbles, small bubbles inside it? Now these objects are used in day-to-day life, but these objects can be further defined in terms of topology, in terms of certain specific characteristics and shapes. So this is something which is called a cut because it has been broken up into two parts. This is called a tunnel because just as through tunnel water peeps in and goes through it through a sponge, the water goes in. And this is which is called void. That means this is empty. We have used these type of concepts in my previous first video on topology, a visual description. But the basic idea is that can we take this cut, the tunnel where water is peeping through it, and a void which is a kind of this kind of a shape where it is empty, and we can use this object to understand them much better. So we can use a further example of a cut or pieces of bread. Then you can imagine that of a balloon and then a kind of a sea through which water pips in and is solid. The question is that is this substances are good enough or based on their shapes how we can understand them. Okay, so classifying the defects, we call it defects in the sense that water is not going through it, the hammer is unable to break it, so obviously it is defect in terms of industrial use. So can we classify those defects or the problems that we saw according to their dimension? So one is that it is called points which are of 0 dimension, lines which are of 1 dimension, and planes which are of 2 dimensions. Lines can be further extended into curves, we know. Planes can be further extended into some spheres, hyperboloids, etc. So what we have just done is that we have identified certain objects which are used on a daily basis. Then we have understood what could be the problems in those objects and how these objects are further extended in order to find and create other shapes. So if we take a kind of a delicious donut which is right in front of you and we extend, I mean to say we stretch that donut into a kind of a torus. So this is the shape when it is stretched. So the donut, once it is stretched, it takes the shape of a torus. But remember that the holes, technically called genus, it always remain. That means the holes really doesn't change. Why I'm making this point, it will be soon clear. Now if I take a kind of a sphere and if I stretch it, then it becomes a kind of an oblate spheroid, right? So why I did this is that we can stretch and shrink topological objects as long as we do not cut them or we glue them in terms of we can use Fevikwik or anything to glue them. So the number of topological features will remain the same. The whole remain the whole, the north pole and the north pole of the oblate spheroid and the sphere remain the same. So indeed the cuts, holes and voids may narrow, but they won't disappear. For example, in case of a donut, it stretched and became more. Indentations may appear, but they won't turn into topological features. This is something central we need to understand. Okay. Now, in every dimension, there are some of those spaces are very special in the sense that they have no end points, right? The edges, which are known as boundary, such as these. So these edges are sometimes also called cycles. For example, this one and this one, these have cycles, and these are called non-cycles or acyclic. So these shapes are, I would say, as well, deformed versions, which was deformed. The circle, as you can see, has become a little bit longer. The torus and then the oblate spheroid, all those things, they are deformed versions and may be collectively called cycles. What makes them special are certain topological features. Meanwhile, objects or figures that they don't have such features are called non-cycles or acyclic. Okay. Now, what we can see from here is that any 2 points from zero cycle, and since this is the simplest of a cut, remember we just talked about cut, we did this in the earlier video also, I have given it in the I button, you can see it. The simplest example of a cut, the latter is a zero-dimensional feature, just like this. Any circle, say for example, any sphere is a 2-cycle, and since it is the simplest example of a void, the latter is a 2-dimensional feature. Any circle or is a 1-cycle, and since this is the example of a tunnel, the latter is a 1-dimensional feature. So these objects, we have used them in order to understand things, that how a cut and a void and a tunnel can be further used into dimensions, and when they're extended, their topological features remains the same, yet the cut or the hole doesn't really change. Okay. So we saw at the very beginning of our study in the first video that we are interested in the visible features of every object, which is the cut gaps, the holes or tunnels, and funnels and void. Now, if we try to describe these features mathematically, right, how do we do that? So, in order to make this this study of a kind of a generic topology, so we do this subsets of Euclidean space X, which is a subset of R of n, and if you use the continuity of function, simple, it looks like this: f x mapping towards y, which is a subset of R of m. And if we can use calculus, we understand via the coordinates f of I is R n of m, and where I is going from 1, 2, 3, 4 variables and so on. So we would be looking basically into what are called the intrinsic properties. The intrinsic properties are the ones which that you can detect from within the object. Now, we need to understand that even though we describe these properties as visible features, our interest is mainly the intrinsic properties. The intrinsic properties are the ones that we can detect from within the object. Now, for example, this is a one-dimensional case, that one you can think just this particle or a worm or anything like that moving through a system of tubes. So you see it is a one-dimensional worm and it goes thing like that. So why I made this illustration? Because the topology of the worm can feel and detect it is limited to the forks of this tube, right? And it may also discover that it can come back to the beginning point of its journey, right? This is an example of a one-dimensional form. Meanwhile, we humans can see the whole thing of being outside in the two-dimensional space. On the other hand, we humans, we cannot tell that whether the surface of the earth is a sphere or a torus if we say, for example, we are covered by a darkness or something. So intrinsic properties are only properties that we hope to capture when we study the topology of a three-dimensional universe, or we are moved out of the properties. For example, if I take this kind of a door, right, and we are walking out in and out simultaneously through another door, which might be upside down, just like this. So the basic idea of giving this illustration is to let you know that intrinsic properties are something which we are really interested in, because extrinsic properties are something until we move out of this surface of earth in a space or something we cannot know. So that would give us a better understanding of the topology. So if you in a room, when you are walking out and simultaneously entering through another door, it can be upside down, that we can only tell once we understand the three-dimensional universe. Okay, so informally, mathematical, what we are trying to do is that a mathematical meaning of topological features of subsets of the Euclidean space. So this is what we call featureless objects. So we will explore the mathematical meaning of topological features through featureless objects. And the big question that arises now in your mind is that why are we making featureless objects? Why is that this object should not have any feature? I am just demonstrating it in the next part of our video. So this is called creating featureless objects, or why do we create featureless objects? I will take a very simple example from our high school mathematics. So you can understand this is basically a triangle, right? This is also a triangle, but it is in an inverted position. We have rotated it. Now again, this is an angle which somehow gives 110 degrees, and this is also inverted. So what I'm trying to make a point is that angles are congruent even they are flipped or rotated. If they are flipped, they will be angle. If they are rotated, they will still be an angle. So this is a rotation in both the cases. The question is that can we devise a tool where all these polygons are featureless? This is very important. Why we are making it featureless? Now, if you have gone to my other videos on topology, I have always said that topology is a generalization of the Euclidean geometry. So until and unless we come out of the specific features of a particularly polygon, for example, an angle, the sides, all those things, then we cannot make it much more general. We cannot make it which is applicable to any manifold or any dimensions of space. So this is the reason that we are trying to find something which is featureless, which won't have a feature, and we can extend those objects to much more broader use. So these polygons, we all know, can be extended further into this kind of weird shapes, and these polygons to any shape. So and congruency is also extended into something which we call featureless objects, a property preserved under homeomorphism. So congruency is something which is very specific to Euclidean space, or a flat space where things happen, but we are trying to generalize it into a featureless object so that it can be used in any part. So this is the reason that we are trying to find out featureless objects. So further example, a torus, and we know that a torus and a cup is basically homeomorphic to each other. Similarly, kind of a cube can be homeomorphic or can be inflated into this kind of a shape, right? So what is happening that when the torus is going into the cup, or the circle is going into these kinds of shapes, which is turning into a kind of a sphere, all we are trying to do is that getting featureless objects which won't have any feature, which will help us to understand topology and create objects which can be used for any coordinates and in any dimensions. Okay, now that we have understood that why do we need featureless objects, the question comes that how these objects are connected between one point to another. Obviously, we need to have points, we have distances. In Euclidean geometry, we calculate modulus distance using Pythagorean theorem. Here, how these objects are connected. Well, first of all, we represent a topological feature of space by X, and by means of cycles of dimension 0 and 1 and 2. So here it is, we can draw them anywhere in X, such as 2 points, circles, and other closed curves. These are few illustrations. 2 points are being connected by line, and there's a circle and a sphere. So all for anything X, for example space, to be a featureless objects of a figure, all of its cycle have to have a trivial sense. All of its circles should be, I would say, there should be a capacity to fill the opening of the cycle, its ability to contain or bound something in X. Okay, so the cuts and gaps, the gaps between 2 points, as we see, can be filled with a curve in X. Very simple, and this is what is called a path connected. Here is how it shows. So a path connected topological space X is a space, just imagine it to be a space where given any 2 points, there exists a continuous path between them. So this is what is called a path connected. So if you're given 2 points, it is just connected by a path. There is something which is called simple connected, but we will talk about it later. So the gap between every 2 points in a space X can be filled with a curve in X. You can see right at the bottom, there is a kind of a different shape. It is connected by 2 points. This is what is called path connected. Okay, now I will take those parts which we learned. So the cuts and gaps, the gap between every 2 points in X, that is 2 points in the space X, can be filled with a curve, and it looks somewhat like this. There's a connected, there's a disconnected. Holes and tunnels, that we have learned that there is a hole, and you remember that water is permeating through it or not. This hole is in every closed curve is filled with a surface, and it looks like this. The hole, there is a surface. Third case, voids and tunnels. The void in every closed surface is filled with a solid, and it looks like this. So you see the torus, and you see the whole void, and we are using a sphere in order to connect it. So these are the 3 examples that when we are talking of path connected and we are trying to fill it up, how this is being done. Isn't it interesting? So if we want to express this, connection, etc. in mathematics, then what we do is that it is simply described as X subset of R of n is called path connected if for any 2 points A and B in X there is a continuous function of interval 0 and 1, and such that Q of 0 equals to A and Q1 equals to B. That is the path connecting these 2 points. So path connected space is a stronger notion of connectedness requiring the structure of a path. Right. So we get 2 intervals 0 and 1, and there is a continuous function such that 0 equals to A and 1 equals to B. Very, very simple. Nothing much to worry about. Okay. Now that we have understood the mathematical description of what is called path connected, and we have understood why path connection is required, and we have also understood that for path connection we need to construct featureless objects. Let us find out in simple words what connectedness actually means. Connectedness means in some sense all in one piece. That means you have to connect all those things together. When a mathematical object has such a property, we say it is connected. You see A and B are connected by this red curve, and here is this A and B 2 points which are not connected. Yes, otherwise obviously it will be disconnected. This is a new definition. When a disconnected object can be split manually into connected pieces, each piece is called a connected component. Sorry. So actually what happens is that there is something called connectedness. There is something called connected space. So anyway, what we are trying to make here a point is that if there are 2 points which has been connected, we call it basically connected. If it is not, it is not connected. Fair and good till now. Okay. Now, filling gaps, when we are trying to fill up those gaps, right? We talked about those filling gaps, is basically can be considered as an ability or a capacity to connect the 2 points to each other. together. Now you understand that when there are 2 points, we can fill up the gap, or we can connect to them by filling through a curve. But what about the other things? So here you see there are the 2 points, they are be connected, so there are no gaps. If this contains dimension to be 0, it is connected by a curve and the dimension is 1, and there are any 2 points which can be connected. So the feature is any 2 points, it is trivialized by, they are connected by, and there is a filling of a curve, the dimension is 1, and featureless, it has got no gaps to be dimension to be 0. The curve is of dimension 1. Yeah. Similarly, if we get a figure like this, which has got no tunnels, that means we are filling up. So there is no tunnel, dimension equals to 2. It is connected obviously by a surface, and the surface dimension is 2, and it can be connected by any closed curve. If you get a figure like this, then it has got no voids. The dimension is obviously 3. I mean to say the solid's dimension is obviously 3. It is connected by a solid which is of dimension 3. This is of dimension 2, and it has got any closed surface. So we can say it in a summarized way that the relation between dimensions, there is a k-dimensional gap, is filled with k plus 1 dimensional object. So any dimension is being filled up with the dimension plus with another dimension. So I hope that these things make clear. So the topological features, that means what are the features that typically one should have? Okay, let us look. The description should include no measuring. Why? Because then the features are preserved under stretching, bending, etc. Right? Second point is that the figure should be verified from inside the object, because we are trying to find the intrinsic meaning. Why that is so? Then the features are independent of how x might be into some y. Third is that the description should be quantitative. Why? Because without measuring, what is left is counting. Now, what do I mean by that is that the first 2 things can be done. It is quite easy, right? But how qualitative it is. So till now we have been able to say whether yes or no, whether connected, not connected, whether it is trivial or non-trivial. But without counting of the features, there is no evaluation of the topology of X, that is a space. This is what we are going to now go a little bit deep, that how we are going to find the quantitative aspect of it, and what is left with the counting. Okay. So we start with the goal with dimension 0 right now, and learning how to count the topological features based on the definition of path connectedness. Now, because the description should be quantitative, we would like to count not the number of cards, but the number of pieces of the objects. Now, you might be asking the reason why we should do this. Why would we like to count not the number of cards, but the number of pieces? The reason is that the former concept is ambiguous. Why? Because we can always say that in order to cut a cake into 4 pieces with 4 cuts, and somebody will say it is of 2 cuts. Right? So what we are now trying to find out, in order to get the description to be quantitative, we would like to count not the number of cuts, but the number of pieces, because cuts counting with number can be very ambiguous and it can be cut in different way. Okay, so there are infinitely many points in each piece. So I mean to say, when we are counting, say for example we are counting, there may be one piece can have infinitely many points in each piece. It would not make sense to count those, as we need to resolve this ambiguity. So we observe that in definition the 2 points are connected to each other by a curve. So it would no make sense to count those, because instead of counting the pieces directly, we count the point. But when we are counting the points, we count 2 of them only once, right? 1 and 2, 2 points AB, we count them only once if they are connected to each other by a path. So this means that we do not count points, but we count classes of points. Here you can see we are counting this one and we are counting this one. So when it is connected with 2 points, we only connect once, right? When it is connected with 3, 1 to 3. So what happens is that we count two of them only once if they're connected to each other by a path, but that actually implies that counting is done based on the classes of points, how many the classes of points are divided, not on the points, because how much will we count? Infinite amount of points, right? So we are dealing with an equivalence relation. We will talk about it, and this equivalence relation is called homology, and the equivalence class, the entire class which deals with this equivalence relation, is called homology of classes. So that would be basically our next point of discussion. So I hope that this video has cleared up the concepts of topology quite clearly. The reason being that as you understand that we understood the need for a featureless object, and we created a featureless object, how the featureless objects are connected through path, and how this path can be defined mathematically, and in order to fill up those gaps, what are the things that we are doing, and in order to count them, we are not counting in terms of numbers but in terms of classes, and that is what counts our homology. So in the next video we would be talking about path connected space, connected component, what is homology, the need for homology, homology classes, and defining and counting in 0 and 1 dimension, and homology as an equivalence relation. Thank you very much. That is all for today's video. Thank you very much for watching this video. All I tried to give is a kind of a illustrative example of topology using less amount of complex set and mathematics. Please do subscribe to my channel Physics for Students. Click on the bell icon to get all the notification from Physics for Students, and as usual I will be waiting for your comments. Please put up your comments and stay happy and stay physically fit and keep on learning physics and mathematics, and very soon I would be coming up with another interesting video. Goodbye till then, and stay at your best. Goodbye.
Thank you for watching this video. We appreciate your time and patience. If you want to connect with us and provide further feedback, comment or suggestions, please email us at contact.physicsforstudents@gmail.com. You can also follow us on Facebook, Instagram and LinkedIn. See you soon in the next video.